Hi, welcome to Problem Solving Expert. This time I will be talking about linear regression, and it will be all of them: simple linear regression, multiple linear regression, and multivariate linear regression. According to Wikipedia, linear regression is a linear approach for modeling. Actually, I want to identify the relationship between one dependent variable and one or more independent variables, which I will call x's. Here I'm having one specific example. Fuel efficiency will be the y, or the dependent variable. Also, I will call it response. And here we are having two independent variables, which are the driver's experience and the truck's age, which I also will call them factors. One example will be, for instance, for simple linear regression, the next one. I will say the expected response, which is the expected value for the fuel efficiency, is equal to a constant V0 plus a coefficient V1, which I also will call it one to those two parameters, times x1. For this specific example, driver's experience can be x1. So I will call to this one x1. I will call to fuel efficiency as a y or response. And this will be a simple linear regression. Another example of simple linear regression would be, for instance, that the expected response, which is the expected fuel efficiency, is equal to the constant V0 plus, let me call it V1 x2. And x2 will be the truck's age. So I can call to this factor x2, which will be the truck's age. Both of them will be simple linear models. By the way, I will call them model, equation, or transfer function. Sometimes I will call them transfer functions. But for instance, if I want to do multiple linear regression, the model can look like this one. It will be, for instance, expected response, fuel efficiency, equal to V0 plus V1 x1, which will be the driver's experience, plus V2 x1 square, for instance, or also it can be plus V3 log of x1. In all of those cases, I am indicating the relationship between one independent variable, but I'm having several parameters to explain the expected response. By the way, the model is linear, but the terms not necessarily are linear. For instance, here I'm having x1 squared, so this is not a linear term. Or I'm having log x1, so that is not a linear term. But the equation by itself is linear because I am adding linear terms. For instance, what will be the multivariate? A multivariate, for instance, will be expected response is equal to V0 plus V1 x1 plus V2 x2, for instance, plus V3 x1 x2, for instance. For this case, I will call it multivariate linear regression because the predictors are involving or are including several, more than one, in this case two, independent variables. x1, which will be the driver's experience, and x2, which will be the truck's age. So, well, basically in this video, I'm going to cover two things. Number one, how to obtain these coefficients or these parameters for the equations from data. I will be using this example, and from the data I will be obtaining the coefficients for the model. And number 2, I will be calculating the coefficient of correlation of Pearson, R, and from there I will be obtaining the R² adjusted. This parameter will be an indicator of how good the equation is predicting or the expected values, how close are from the observed values. The better the model, the higher the R² adjusted, the higher the coefficient of correlation will be. Basically I will be talking about just about those two things during this video. There's too much to talk about regression, and specifically linear regression, but in this video I will be talking about those two things. Well, let's start obtaining the coefficients for a simple linear regression. That's the next thing to do. Simple linear regression. Well, for simple linear regression, I will be using this data, and specifically I want to develop or obtain the coefficients or the parameters for the relationship between x1, which is the driver's experience, and the response, or y, which is the fuel efficiency. So the model that I want to obtain is the expected response, the expected fuel efficiency, is equal to V0, which is a constant, plus V1, the first parameter, or another coefficient, times x1, and x1 will be the driver's experience. Using the data that I'm having, the data for fuel efficiency and driver's experience, the objective is to obtain the coefficients of the model or the parameters of the model, V0 and V1. For any linear regression, the way to obtain the coefficients or the parameters is using some matrices, operations with matrices, which is matrix B is equal to X transpose Y, X transpose X inverse. Well, let's do that. So for the matrix B, it will be something like this one. Matrix B is equal to B0 and B1 for this specific example. Matrix X will be X is equal to this is driver's experience will be the X1, which will be the matrix X, and also we are obtaining B0. So I want to obtain there the term that is going with B0 and the term that is going with B1. With B1 we are having X1, and X1 are all these values: 8, 13, 0, 11, 5, 5, 2, and 15. So that is the column for B1. And what will be the column that is going with B0? Well, actually here we are having a number 1. So for this specific example, we are having 1, 1, 1, 1, 1, 1, 1, 1. So basically this is matrix X. Well, at this point I have defined matrix B, which is this one, matrix X, which is this one, and now I have to define matrix Y. And matrix Y basically is the fuel efficiency, and we are having the observed values for fuel efficiency. So matrix Y, it will be Y equal to the first value of fuel efficiency, which is equal to 2.54, and that will be the first value, 2.54. The second value will be the second observed value for fuel efficiency, which is 1.31, and it will be 1.31. And so on. I will continue writing the rest of the data for the fuel efficiency, which will be okay? Well, now I will start doing the calculations. The first calculation to do is to multiply x transpose times y. I have matrix X, but I do not have X transpose. Transpose basically means to convert columns into rows or rows into columns. Then X transpose Y, it will be X transpose Y, it will be equal to the first row will be the first column, 1/8. The second row, the second column, 1/13. Third row, third column, 1/0, and so on. This is matrix X transpose. Now I have to multiply this one times Y, and matrix Y will be that one, which is okay. Now let's do the calculations. Then X transpose Y, we are going to multiply the first row times the column, which it will be 1 times 2.54 plus second with second, 1 times 1.31 plus third with third, 2.03, and so on. Okay, that is the first row times the values of matrix Y. Now the second row times those values as well. Well, I will be using the calculator. The first value here, the first term will be 8 times 2.54, and it will be plus the second times the second, 13 times 1.31 plus 0 times 2.03, and so on. Okay, now I will be doing the sum of all these values for the first number, and the sum of those values for the second one. Then it will be X transpose Y, 2.54 plus 1.31 plus 2.03 plus 1.85 plus 1.85 plus 2.26 plus 1.95 plus 1.16. Let's do that. $14.95. Now let's obtain the second, which is 20.32 plus 1703 plus 0 plus 20.35 plus 9.25 plus 11.3 plus 3.9 plus 17.4. $99.55. Okay, that will be the matrix X transpose Y. I will copy that result, X transpose Y, which is equal to 14.95 and 99.55. Okay, we have the first calculation. Now I will be calculating x transpose x and inverse. Later I will be inverting this result. So first I will be doing x transpose x, and it will be something like this one, x transpose x. As I have said, the x transpose will be matrix x, but I have to convert the rows into columns, or vice versa. So x transpose x will be the first row, now is the first column, 1A. Second row, second column, and so on. And I have already x transpose, now I multiply times the x, which is equal to this matrix. Okay, let's do the calculations. Then x transpose x will be, for the first row and the first column, this is first row and first column, I will be using the first row and the first column, which means that I will be multiplying 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1, and so on. So it will be something like this one. Okay, and that is the result for the first row and the first column. Now, for the first row, second column, I will be using the first row and the second column. Then I will multiply 1 times 8 plus 1 times 13 plus 1 times 0 plus 1 times 11, and so on. 1 times 5, and so on. So the result, it will be okay. Now I will calculate the second row and first column. I will be using the second row and the first column. 8 times 1 plus 13 times 1 plus 0 times 1, and so on. So I will get something like this one. And finally, I will be obtaining the second row and the second column. So I will be using the second row and the second column. So it will be 8 times 8 plus 13 times 13 plus 0 times 0 plus 11 times 11, and so on. And well, I will be using the calculator to obtain each of those. So, for the first one, okay. The next thing to do is basically doing all of these sums, this and that and that and that. So let me do that. I will erase this. X transpose x is equal to 1 plus 1 plus 1 plus 1 plus 1, and so on, is equal to 8. The second one, 8 plus 13 plus 0 plus 11 plus 5 plus 5 plus 2 plus 15. Next one, sum of 8 plus 13 plus 0 plus 11 plus 5 plus 5 plus 2 plus 15. And finally, 64 plus 169 plus 0 plus 121 plus 25 plus 25 plus 4 plus 225. $633. I will copy that calculation. X transpose X, that matrix is equal to 8, 59, 59, and 633. Okay, well, I already have X transpose Y and X transpose X. But the next step is this second matrix, I have to invert that matrix. Well, let's proceed to do the inverse or inverting that matrix. X transpose X is equal to 8, 59, 59, 633. But now I will have 1s on the diagonals and 0 for the rest. So it will be 0, 0, and 1. I will do the necessary calculations to make sure that this matrix, it will be on the left side, and the resulting matrix on the right side, that will be the inverse of the matrix. So for instance, if I want to make this 8 a 1, because I want to make this 1, make this 0, make this 0, and make this 1. So, and by the way, I have to work always by rows. Well, you know, if I want to make this 8 number 1, I have to divide the row by 8. Then it will be row 1 new is equal to row 1 divided by 8, divided by 8. And it will be 8 divided by 8 is equal to 1. 59 divided by 8, 7.375. 1 divided by 8, 0.125. And 0 divided by 8 is 0. Row number 2 will be exactly the same. 59, 633, 0, and 1. Okay? Well, we are done then with the first value, which is converting this 8 into a 1. I have to move by column. Then the next step is to convert this 59 into a 0. We always should take as part of the calculations the pivot value, which is this 1. So it's not valid to say that row 2 minus 59, and with that one we will obtain 0. But we have to make a reference to row number 1 as well. So for this example, it will be row 2 new is equal to row 2 minus 59 row 1. Okay? Well, let's proceed. The first value is the same. I'm not affecting the first row at all. But the second one, it will be 59 minus 59 times 1. And that will be equal to 0. The next one is the same, 7.375. The next one, it will be 633 minus 59 times 7.375. And that value would be this one. I will be using the calculator. $197.875. The next one, it will be the same, 0.125. Next one will be row 2, 0 minus 59 times row 1. And that is equal to negative 7.375. Next is 0. And finally, 1 minus 59 times 0, which is equal to 1. Okay. Well, we are done with the first column because we have converted the first column into a 1 and a 0, a 1 and a 0. Now the next step is to convert this 187.875 into a 1. And well, I will repeat the process. It will be row 2 new is equal to row 2 divided by 197.875. Then it will be 0 divided by 197.875 is 0. The next is the same, 7.375. 187.875 divided by 187.875, it will be a 1. Next one, it will be minus 7.375 divided by 187.875, and it will be 0.037271. Okay, 1 divided by 197.85. 0.0050537. Okay. Okay, then the last step to convert this 7.375 into a 0. I have to use also as a reference the pivot value, which is the 1. In this case will be row 1 new is equal to row 1 minus 7.375 times row 2. And well, let's do that. 1 minus 7.375 times 0 still is 1. Second one, 7.375 minus 7.375 times 1, that is 0. This is 1. We are done. Now, the next one, it will be 0.125 minus 7.375 times minus 0.037. .4. The next one will be row 1, 0 minus 7.375 times 0.00505. Negative 0.37271. And finally, that one, 0.0050537. We are done. This part, which is ones on the diagonals and 0 for the rest, now they are at the left side. Then the X transpose X inverse, X transpose X inverse is this matrix on the right. And well, I will copy that one to here, and I will state X transpose X inverse is equal to 0.4 minus 0.037271 minus 0.037271 and 0.0050537. Okay, that is the X transpose X inverse. Next step, I have to multiply X transpose Y, which is this matrix, times X transpose X, which is inverse, which is this matrix. Let's do that. Matrix V, X transpose X inverse X transpose Y. And I have said that X transpose X inverse is equal to 0.4 minus 0.0372771 minus 0.0372771 0.0050537 times X transpose Y times 14.95 and 99.55. Then it will be matrix V. The first row and the first column, 0.4 times 14.95 plus minus 0.37 times 99.5. Now for the second row, it will be the second row and the column, which is minus 0.0375 times 14.95 plus 0.005 times 99.55, which is matrix V. Let's do the first part. $5.98 minus 3.708. Let me do, well, 708. And the second one is negative 0.5572 plus and that is equal to 2.272 minus 0.05435. Well, initially I have said that matrix B is equal to B0 and B1. And now I have said that matrix B is that one, which is 2.272 and minus 0.05435. That means that B0 is equal to 2.272 and B1 is equal to minus 0.05435. That means that the model is equal to the expected response, which is the expected fuel efficiency, is equal to 2.272 minus 0.05435 times x1. In this case is the experience of the operators experience. And well, that is the model that we have created, and that is a simple linear model. How good is this linear model? The driver's experience is significant, is really affecting the driver's experience to fuel efficiency. Are we missing factors, or are we missing terms? Well, at this point, we cannot answer to any of those questions. In order to address those questions, we have to identify how good the model is fitting to the observed values. So how good the expected, or how close are the expected values obtained from the model to the observed values, which is this data that we are having. How can we do that? Using a coefficient of correlation. And that is the next step. I will be calculating the coefficient of correlation of Pearson for this model and this data that we are having. Let's do that. We have already obtained our model to predict the expected fuel efficiency depending on the driver's experience. The question is how good this model is, how well is fitting to the observed value, which is the fuel efficiency. Well, in order to determine that, I will be using R, which is the coefficient of correlation of Pearson. Coefficient of correlation of Pearson can go from 0 to 1, or which is the same thing, from 0% to 100%. The higher the value will be, the better will be the fitting or the correlation between the expected values and the observed values, the better the model is. Well, to determine that, we have to use this equation, which is using a covariance and a multiplication of variances. Variances of what and covariances of what? Well, variances of expected values and observed values, covariance of expected values and observed values. We already have the observed value of fuel efficiency. Now the next step is to determine the expected value for fuel efficiency. And the expected value will be obtained from the model, from the equation that we just got. In this case, for the first value, what will be the expected value? Well, I will be saying that the expected fuel efficiency for the first value is equal to 2.272 minus 0.05435 times X1, which is driver's experience. For the first value, the experience of the driver is 8 years of experience. Multiplying this, we are obtaining that the expected value is 1.8372. And that will be the first value for the expected, 1.837. Let's do the second value. For the second value, it will be the same process. We are having the equation 2.272 minus 0.04535 times driver's experience, which is 13. In this case, the expected value will be 1.565. Well, and that will be the expected value, 1.565. Third value will be same thing, 2.272 minus 0.05435 times 0, which is 2.272. 2.272. And so on. I will continue doing the calculation for the rest of the driver's experience values. Well, we already have the observed values and we are having the expected values. The more similar they are, or they will be, the higher the coefficient of correlation will be. So as we can see here, there are some differences between the observed and the expected. So personally, I'm not expecting a very high R square adjusted, which I haven't talked about that one yet, but a high coefficient of correlation of Pearson, I'm not expecting that. Still, I will continue with the process doing the analysis. As you can see here, we need the sum of the expected values square. Then I have to obtain the expected values square. Also, we need the sum of the observed values square. I have to obtain the observed values square. And also I need the sum of the expected and the observed, which is the expected and the observed. Well, I will be doing that. So the first value is basically to obtain the observed square, which is 2.54 square is 6.4516. 6.452. 1.31 square, which basically will be 1.7161. And so on. I will continue doing that. Later, also, I will be doing the expected value square, 1.837 square, which that one will be equal to 3.375. And also expected times observed, which is multiplying 2.54 times 1.837, and that one will be 4.666. I will continue with the rest of the calculations. I have done all the necessary calculations to obtain the coefficient of correlation of Pearson. Then I will proceed to do the rest of the calculations. The first term, it will be the variance of the expected values, and it is the sum of the expected values square. Here I'm having the expected values square, and the sum of that is 28.595 minus the sum of the expected values. Here we are having the expected values, and the sum of that is 14.969 square divided by the number of values. And here we are having 8 values. We are having 1, 2, 3, 4, 5, 6, 7, 8. And that is the value that I will put here, which is n equal to 8. Now, I will obtain the variance of the observed values, which is observed values squared, sum of that. Observed values squared, and sum of that is 29.389 minus sum of the observed values, which is the first column. So here we are having the observed values, and the sum of that is 14.95. So 14.95 square divided by the number of values, which is 8. And the covariance is the sum of expected times observed. Here we are having expected time observed. The sum of that is 28.556 minus the sum of the expected values sum, 14.969 times sum of the observed values, which is again the first column. Observed value, sum of that is 14.95, so it is 14.95 divided by total number of values, which is 8. Okay, I will proceed to do those calculations. Here we are having the results of each of those calculations, which is all what I need to obtain the coefficient of correlation of Pearson. In this case, it is the R is equal to the covariance, and the covariance is 0.5819 divided by the variance of the expected values. The expected values is 0.5945 times the variance of the observed values, which is 1.4515, and the square root of that. Okay, I'll proceed to do the calculations. We are having a coefficient of correlation of 0.6317, which is the same thing than 63.17%. The first question is there a linear relationship between the response, which is fuel efficiency, and driver's experience? Well, the answer is it depends. It depends on what? Well, what we have to do is to take a look to a table, and depending on the number of values that we are having, if that value, that coefficient of correlation is greater than the value of the table, then we can conclude with 95% confidence level that there is a linear relationship between those two variables. But if this value is smaller than the values of table, then the conclusion will be there is not enough statistical evidence to conclude that there is a linear relationship between those two variables. So let's take a look to the table. Taking a look to the value of R, minimum required to conclude that there is a linear relationship between two variables. For n equal to 8, the R necessary to conclude with 95% confidence level that there is a linear relationship is 0.707. Since the coefficient of correlation that we got is 0.63, which is smaller than 0.707 coming from tables, the conclusion is there is not a linear relationship between those two variables, between the driver experience and the fuel efficiency. Now, the question is, well, Okay, there is not a linear relationship, but is there any relationship between this X, which is driver experience, and the fuel efficiency? Well, to answer to that question, we have to take a look to the R-squared adjusted. Also, the question that we want to answer is, do we need more parameters or more factors to have a good prediction or a good model to predict the fuel efficiency? Also, we can take a look to the R-squared adjusted. So let's talk about R-squared adjusted. For the R-squared adjusted, it is necessary to have the coefficient of correlation of Pearson, which is just what we have gotten, which is 0.6317. Number of values, we are having 8 values, and P is number of parameters in the model. In the equation that we are having, which is the expected fuel efficiency equal to 2.272 minus 0.05435 driver's experience, we are having 2 parameters. The first parameter is the constant, V0, which is this value. And the second parameter is this one, which is related to the driver's experience. So P equal to 2. Then all what I have to do is to use that formula. The R-squared adjusted is equal to 1 minus 0.6317 square times N8 minus 1 divided by 8 minus 2 parameters, 2. Okay, I'll do the calculations. Here we are having our R-squared adjusted, and which is 29.9%. And we can have 2 pieces of information from that one. Number 1, if the R-squared adjusted is greater than 20%, that means that the factor that we are including in the model is a vital factor. If the R-squared adjusted is between 10% and 20%, that is an important factor. If it is between 2, 3% and 10%, that is a trivial factor, and the smaller than 2, 3% is a non-significant factor. Well, that is the first conclusion. For this example, since the R-squared adjusted is greater than 20%, almost 30%, then that means that driver's experience is a vital factor for fuel efficiency. That's a good thing. We have discovered a vital factor for fuel efficiency, which is the driver's experience. Now, second piece of information. If the R-squared adjusted is greater than 80%, that means that we are not missing any vital factor and significant term in the model. If the R-squared adjusted is smaller than 60%, that means that certainly we are missing at least one vital factor and or significant term in the model. Since this value is smaller than 60%, that means that although the driver's experience is a vital factor, we are missing other vital factors and terms. So we should look for other terms and or other factors to identify what is missing, because we are not having a good model. Well, with all of this, we have already concluded that this is a vital factor, but we are still missing factors and or terms, and the relationship that we are having between those two variables is not linear. Because of that, now I will proceed to talk about multiple linear regression, and that's the next step. At this point, I have concluded that there is a strong relationship between driver's experience and fuel efficiency because the R-squared adjusted is greater than 20%. But also I have concluded that the relationship between those two variables is not linear because the coefficient of correlation of Pearson is smaller than 0.707, which was the value that we got from a table. So then, if it is not linear, how is that relationship? Is it an exponential relationship, a cubic relationship, a logarithmic relationship, reciprocal relationship? What kind of relationship is there between the driver's experience and the fuel efficiency? Well, recommendation. We can take a look to a scatter plot. If we take a look to a scatter plot, we can get a clue, we can get an idea of what kind of relationship there can be between those two variables. And that's what I will be doing next. I will do a scatter plot. So here we are having on the axis of y the fuel efficiency and on the axis of x the driver's experience. And well, all what I will be doing is plotting those two values. 8 years of experience, 2.54. 8, 2.54. That will be something like here. Second one, 13, 131. 13, 131. Maybe something like this one. 0, 203. 0, 203. Maybe something like this one. 11, 185. 11, 185. Maybe something like this one. 5, 185. 5, 185. Maybe something like this one. 5 again, 226. 5, 226, which is something like here. 2, 195. 2, 195. It's something like this one. And 15, 116. 15, 116. Although it's not that clear, apparently, here we are having something like this one. Let me try to guess somehow. We are having something like this one. And what means that? That is going up and then going down. So something like this one. So that means that maybe that is a quadratic relationship. If we take a look to your screen, you can see that depending of the form of on the graphs, on the scatter plot, it can be a linear relationship, a quadratic relationship, a reciprocal relationship, a logarithmic relationship, etc. In this case, since we are having something like that one, maybe we are having a quadratic relationship, and that means that the model, the equation that maybe we should try is equal to y of expected, which is the fuel efficiency, equal to B0 plus B1 x1, driver's experience, plus B2 x1 square. Again, driver's experience, but square, because that will be a quadratic. Well, what do we have to do to obtain the coefficients for this equation, which is multiple linear regression? Well, using exactly the same mechanics. And that's what I will expose next, defining the matrices to obtain the coefficients of this for this equation. Let's do that. I have said that to calculate the parameters of the equation, all what we have to do is to do this calculation. Matrix B is equal to X transpose X inverse X transpose Y. And well, all what I have to do is to, or all what I will be doing is to define those matrices. For this example, matrix B is equal to B0, B1, and B2. Matrix Y, which is equal to the values of the fuel efficiency, which are all of those values, the same that we got on the previous one, 2.54, 1.31, 2.03, 1.85, 1.85, 2.26, 1.95, and 1.16. And matrix X will be equal to the first one, which is the one that goes with B0, the ones that goes with B1, and the ones that goes with B2. For the first one, as I have said before, here we are having a 1. Then it will be 1 here. 1, 1. B1, it will be X, which is 8, 13, 0, and so on. And the one that goes with B2, which is x1 square. x1, 8, square, 13 square, 0 square, 11 square, 5 square, 5 square, 2 square, 15 square. And that is matrix X. And now all what we have to do is to do all these calculations. X transpose X, the result of that inverse, X transpose Y. I will be doing that. Okay, so here we are having the result for matrix B. That means that for the equation, the expected value for fuel efficiency is equal to B0, which is 1.881, plus B1 plus 0.1248, which is this one B1, for X times X1, which is times driver's experience, plus B2, which is not plus, but actually is minus 0.1178, times driver's experience square. Okay, here we are having the equation. Now, how good is that equation to fit to the observed values? We have to do the same thing that we have done before, which is obtain the coefficient of correlation of Pearson, R, and then the R square adjusted. So using this equation, I will be obtaining the expected values for fuel efficiency. And later, I will compare the expected values with the observed values using the variances and the covariances. I will be doing that. For this quadratic equation, we are having that the coefficient of correlation of Pearson is 85.5%. And taking in consideration the number of parameters of the equation and the number of values of data that we are having, the sample size, we are having the R square adjusted of 62.47%. Before it was 29.9%, now it is 62.47%. the correlation or the adjustment between the expected and the observed is much better now. Now the equation is fitting in a better way to the observed values, which means that it is a good idea to include a quadratic term. The relationship was not linear, but is closer to, we can say that it's better to say that this is a quadratic equation. Still, since the coefficient of correlation is very close to 60%, no greater than 80%, very likely we are missing a vital factor. So we need to explore some other potential factors, and perhaps the other factor is Trox's age. And that's what I will be doing now. I will be doing multivariate linear regression, because I will include in the model not just the driver's experience, but the Trox's age. Let's do that. Doing the simple linear regression between Trox's age and fuel efficiency, this is the equation that we get. And this is the R-squared adjusted, which is 15.06%. As I have said, since the R-squared adjusted is between 10% and 20%, that means that this is an important factor. We already know that driver's experience is a vital factor. Now, what I want to do is to put together both factors, both variables, which is driver's experience and Trox's age, both as part of the equation, to try to obtain a model to predict the fuel efficiency. And then I will be doing a multivariate linear regression. First, I will propose the next model, and which is the expected value for fuel efficiency equal to B0, which is the constant, plus B1 times, times X1, which is the driver's experience, plus B2 X1 square, which is the driver's experience square, plus B3 X2, which is the Trox's age. Here we are having two factors, X1, driver's experience, and X2, which is Trox's age. That's why this will be a multivariate linear regression. We are adding terms, so that's why it's a linear equation. Well, how then the matrices will be? Because keep in mind that matrix B is equal to matrix X transpose X, and the inverse of all of that, X transpose Y. Well, what is the matrix B? Matrix B will be, matrix B is equal to B0, B1, B2, and B3. Matrix X, the matrix X is equal to the term that is with B0, the term that is with B0, B1, B2, and B3. In this case, the one that goes with B0 is 1, so here we are having 1. The one that goes with B1 is X1, which will be driver's experience. So it will be these values 8, 13, 0, 11, 5, 5, 2, and 15. The one that goes with B2, which is X1 squared, which is X1 squared, 0 squared, 11 squared, 5 squared, 5 squared, 2 squared, and 15 squared. And the one that goes with B3 is x2. x2 is strokes h. Then the values will be 1, 13, 0, 9, 15, 7, 8, 7. And the matrix that we are still missing is matrix Y. And matrix Y is the same that we have used for the previous exercises, which is the fuel efficiency, which are the values of Y. And those values will be the ones that will be part of matrix Y. Okay, all what we have to do is to do the calculations with the matrices X transpose X, the result of that inverse, then X transpose Y, and multiply those two to obtain matrix P. I will be doing that. Okay, we are having here matrix B, which means that then the equation, the transfer function, the model is expected fuel efficiency is equal to B0, 2.03, 27.4, plus B1, 0.196.4 times X1, which is driver's experience, plus B2, which is minus 0.1497 times driver's experience square, plus B3, which is minus 0.05040 times X2, which is the age of the truck. Same question. How good is this model? Well, I will be calculating the expected values for each of these values with this driver's experience and this truck's age. What will be the expected value? I will be doing just the first one, and later the rest I will be doing the calculations by myself. For instance, the expected value for the first value is equal to 2.03274 plus 0.18964 times X1. X1 for the first value is 8 minus 0.1497 times 8 squared minus 0.05049 times X2, which is 1. Then the expected value when we are having 8 years of experience of the operator and 1 year old of the truck is the next one. Let me do those calculations. Then, for the first value, which is with 8 years of experience of the driver and 1 year of age of the truck, the observed value was 2.54 kilometers per liter of fuel efficiency. The expected value using the equation that we have obtained, the multivariate equation that we have obtained, the expected value is 2.541371. As you can see, the observed 2.54 and the expected 2.5413, they are very, very close each other. Doing the rest of the process to obtain the coefficient of correlation of Pearson and then the R-squared adjusted, we got that the R-squared adjusted for this equation and the observed values is 99.99%. Since this coefficient is greater than 80%, that means that we are not missing any vital factor factor nor any significant term on the model. So now we are having a very good model. And well, basically that's it for this video. In another video I will be talking about some other tests to check if we have done a good analysis, if we can trust on the analysis, taking a look to the residuals analysis, and but well, that will be in another video. So that's it for now. Thank you very much. Have a good one.